Hello there. In this section of the course, we're going to learn a little bit more about acids and bases. Now, hopefully you recall acids like lemon juice or vinegar are solutions that you would place low down on the pH scale, which hopefully you might remember from grade 10. So you find your acids down here on the pH scale. And bases like baking soda, if you dissolve that in water, or bleach would be higher up on the pH scale. Bases on this end. And in between you have things like water that are neutral on the pH scale. So we're going to learn a little bit more about this pH scale, where all these numbers come from, and how they're related to acids and bases, and how they relate to equilibrium, which is why it's in this section of the course. So we'll start with acids. There are several definitions or ways to define an acid. We're going to go with the Arrhenius definition of an acid to begin with, and that is that acids will ionize, so they're molecules that become ions and form these H+ ions in solution. So you can represent that with the acid here giving up a hydrogen ion. Now, a hydrogen ion usually doesn't stay by itself in an aqueous solution. It'll stick to a water molecule, and you get this H3O character here that we call hydronium. And so this hydronium ion is what makes a solution acidic. The more of those it has, the more acidic it will be. However, it can be a lot easier and more simple to represent the ionization of an acid as just separating the acid ion part from the hydrogen ion into these two different pieces. So, of course, a classic one being hydrochloric acid. So you take off the hydrogen and you take off the chlorine. Make sure you have the right charge. They're all dissolved in water, and that would be the ionization of hydrochloric acid. Here's sulfuric acid. You could do this one at a time. You can show a hydrogen ion coming off, and then HSO4 minus like that. Or you could show both of them coming off as eventually happens. So for Arrhenius bases, we're going to start with substances that are already ionic. And so instead of ionizing, they're going to dissociate, which means they separate into their separate ions. And this time you're going to get hydroxide ions in solution, and that's what makes it basic. So most examples will have metals with these hydroxide ions on them. And so when you separate them, you're going to get the positive metal ion, and you're going to get a negative hydroxide ion. And so an example here is potassium hydroxide, and you're going to separate that into potassium ions that are aqueous, and hydroxide ion, also aqueous. And then if we have magnesium hydroxide, same thing. You get a magnesium ion, has a 2+ charge, AQ, and then 2 hydroxides this time. So if they were equal concentration, the magnesium hydroxide would be more basic because you end up with 2 hydroxides for every one that dissolves. Alrighty, so now that you have an idea of what acids and bases are referring to, let's look at the scale. So the pH scale is what we use to distinguish between different acids and bases. And so the P stands for power, like an exponent value, and H is hydrogen, as in the ions. And so to get the pH value, what you do is you take the concentration. So if you remember, the square brackets means concentration of the hydrogen ions, and you're going to take the negative logarithm of that. And so as you recall, a logarithm is the exponent that you put on the base of 10 in order to get a value. And so if you have a hydrogen ion concentration of 4.3 times 10 to the negative 4, so you're going to have a pH that's somewhere close to -4. So if you punch this into your calculator, negative log, and this value here in for the hydrogen ion concentration, it spits out 3.37, because it's not exactly like 1 times 10 to the negative 4, right? And then for the reverse, what you do is if you want the hydrogen ion concentration from the pH value, you take the value of 10. It's usually a second function of the logarithm button on your calculator. And so you say 10 to the power of whatever the pH is, and switch the sign to a negative. So if you say, if you want the hydrogen ion concentration, it's going to be 10 to the negative 8.4 on your calculator, and then it will give you 3.98 times 10 to the negative 9 moles per liter. So, oh yeah, this should have moles per liter as well, because I missed putting that in. So yeah, one other note, when you're using your calculator, they often only have 9 or 10 digits, and sometimes these values get a little truncated. For instance, when I punched this into my calculator, it gave me 0.0000000, 1, 2, 3, 4, 5, 6, 7, 8, and then that. And it was just chopped off the rest of the number. You can see that it's almost a 4, right? But the only way I could see that would be multiplying by 100 or 1,000, so I could see some of the extra digits that were off the end of the calculator. So just some calculators have just chopped those numbers off rather than rounding them, and so it's good to multiply by 10 or 1,000 so that you can see what the extra digits are in there. Okay. So now that we have this measurement of hydrogen ion concentration that's related to logarithms, you end up with a logarithmic scale. A 0 on the logarithmic scale means 1 times 10 to the 0 on the concentration, which is 1 mole per liter. A 1 on the scale is going to be 0.1 moles per liter. A 2 on the scale is going to be 0.01 moles per liter, and so forth until you get way down to the end here, which is 14, which means it's going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros, and then a 1 moles per liter. And so you can see the extreme range of concentrations going from fairly concentrated down to very, very weak on this scale. And so that makes the logarithm scale a lot more useful. And then each increment on the log scale represents a tenfold difference in the concentration of the ions. So if you're going up on the scale, that means the concentration is going to go down. So you're like dividing by 10. And if you're going down on the scale, that means the concentration is going up, and you can multiply by 10. So you might have considered that maybe earlier on, maybe in grade 10 when you were doing pH scale. And now that you have this little bit of math that we did, you can understand why. So it turns out, even though it's not as commonly used, that you can do a pOH scale in the same way using the concentration of hydroxide ions in just the same way that we did with the hydrogen ions. And so pOH value will be the negative log of the hydroxide concentration. And if you want to get the hydroxide concentration, you say 10 to the negative pOH value related to that acid or base. So if you have a concentration of hydroxides, say from a base, and you've worked out to be this number of moles per liter, if you punch that into your calculator, you say negative log, and then you put that value into your calculator, you will end up with a value of 3.66. Of course, no units for that. And then if you want to do the reverse, if you want the hydroxide ion concentration from the pOH, you would say 10 to the negative 11.2 for this value, and it would spit out 6.31 times 10 to the negative 12 moles per liter. And so again, you would end up with this scale with a huge range. At one end, you're going to have things that are very basic and have high concentration, up to 1 mole per liter on the scale of hydroxide ions. And then down at the other end, you've got the really weak ones. So on a 14 on the scale is really low concentration of hydroxide ions. And of course, if you convert it into the concentration, it's that teeny tiny number of hydroxide ions. So exact same thing, just using hydroxide ions. It's a lesser used scale, but works the same way. So you might be asking yourself, why would water be halfway through either of these scales? How come the pH of water is a 7? Where do these hydrogen ion or hydronium ions come from in pure water? Or why would the pOH of water be 7? Where would these hydroxide ions be coming from pure water? So that's where the equilibrium comes in, and we can make sense of that now. So if you have some water, water will actually form an equilibrium with itself, whereby some water molecules give up a proton or a hydrogen ion to another water molecule. And once it gives up a hydrogen ion, what it ends up being is a hydroxide ion, right? And you would end up with hydroxide ions in your solution from just pure water. And also, you're going to end up with the same number of hydronium ions from that same water. And so if you simplify that, of course, if you get rid of the hydroniums and the other water molecule here, it just looks like the water is being ionized to become those two now familiar ions for acids and bases, right? So pure water will produce both hydrogen ions and hydroxide ions in equal quantities, right? One of these hydrogen ions is going to come off and go over to the other water molecule. You end up with hydroxides and hydroniums, which we can simplify to be hydroxides and hydrogen ions. So when it does that, under standard conditions, the amount of hydrogen ions you will get is 1 times 10 to the negative 7 moles per liter in a sample of water. And of course, with that negative 7, that changes it to a pH of 7 for that pure water. So continuing on from that, since there's an equilibrium, there must be an equilibrium constant. We're going to leave the liquid part out of the equilibrium constant, of course, and that means that we only have stuff on the right side here and no left side, which means we just have these two to worry about for our equilibrium constant. This constant is given the symbol Kw, surprise, surprise, W for the water, and the concentration of both those ions, the hydrogen and the hydroxide, will be the same. And so you end up with 1 times 10 to the negative 7 moles per liter for the hydrogen ion, and then 1 times 10 to the negative 7 moles per liter for the hydroxide ion. And if you multiply the two of those together, you end up with 1 times 10 to the negative 14 for the both of them together. And so that is your equilibrium constant for water under most conditions, and you can use that to work out unknown values related to acids and bases, as I'll show you in a minute. So the last point to include here is that when you have this equilibrium with water, you got the water and it is in equilibrium with hydrogen ions and hydroxide ions. If you make something acidic and increase the amount of hydrogen ions, if you increase this, that is going to drive the equilibrium that way, of course, and decrease the amount of hydroxide ions. And then vice versa, if you, say, put a base into your solution that increases the hydroxide amount, that is going to cause the equilibrium to shift and reduce the hydrogen amount. So there's an inverse relationship between these two, between the hydroxide and hydrogen ion concentrations. They're only equal at a pH of 7, where they both match. And it's like both of the scales are inverse of each other. The higher this one is, the lower this one will be, and the vice versa. The higher this one is, the lower this one will be. And so you can stack the two scales onto each other, and you can always work out the other value if you know one of them. They're always going to add up overall to 14, right? 14 and 0, 13 and 1, 12 and 2. And so that's pretty handy if you want to be able to quickly convert between the scales. You can always get a pH from a pOH value and vice versa. And that's how we end up with a scale where you have your acids on the one end here and bases on the other end. And in between is our neutral value of the water. So it doesn't mean that there aren't any hydrogen ions in a base. Let me get bases here. It just means there's less, right? This is hydroxide ion concentration, which increases. And then conversely, your hydrogen ion, which I should use a different color, is going to decrease, right? And on the other side, you have a higher concentration of hydrogen ions and a lower concentration of hydroxide ions. But they are in balance with each other according to this equilibrium that's always going on whenever you have water. Okay, so let's apply some of those relationships that we've learned throughout this lesson in order to work out any of the missing values in this little table. So first of all, we're given a hydrogen ion concentration in this first sample of 2.2 times 10 to the negative 4 moles per liter. An easy thing to do would figure out the pH from that, right? We've done that before. So let's say the pH equals the negative log of that value, 2.2 times 10 to the negative 4. And when you do that, what comes out is 3.66. Great. That goes in here, 3.66. And then the easy thing is that you know that the pH and the pOH always have to add up to 14. So pOH for this is going to be 14 minus the 3.66. And that equals 10.34. So 10.34. Then if we want to figure out the hydroxide concentration, we've got the pOH. A simple way to do that then is the hydroxide concentration is going to be 10 to the negative 10.34. And if you put that into your calculator, you end up with 4.55 times 10 to the negative 11. 4.55 times 10 to the negative 11. There you go. Now, the reverse. Over here, we've got ourselves a pOH value. And so it's pretty easy to get the pH from that one. So we'll say 14 minus 2.6 for our pOH. And that comes out to be, sorry, that was the pOH. We want to get the pH. And that comes out to be 11.4. So really basic. 11.4 is the pH. We can then take that pH and get the hydrogen ion concentration, this guy. So we'll say hydrogen ion concentration is 10 to the negative 11.4, and that comes out to be 3.98 times 10 to the negative 12. So 3.98 times 10 to the negative 12 moles per liter. So we could do the same thing with our pOH value here, but just to mix things up, I'll remind you that the equilibrium constant for hydrogen and hydroxide equilibrium is 1 times 10 to the negative 14. And so if we want the hydroxide ion concentration, we will take 1 times 10 to the negative 14, and we'll divide it by the hydrogen ion concentration, which was 3.98 times 10 to the negative 12. And when we do that, it comes out to 2.51 times 10 to the negative 3 moles per liter, and that would go in here. Yeah, moles per liter, moles per liter. Great. So you see there's a bunch of different relationships and more than one way in which you can solve for these things. And it just takes a little practice, and you'll have them in your pocket and toolkit to be able to do this with any acidic or basic solution. All right, hope that helps. We'll talk to you soon.